Let's talk about derivatives. And what I'm going to do is I'm going to define the derivative as a function, because that's what a derivative is. We can actually take a function, find its derivative, and that derivative is in itself a new function. So we can also take the derivative at a single point. We can look at what is the instantaneous rate of change or slope at a single point along a curve. But what we can also do is just generalize that, look at the entire curve and say, what is its slope in generality? What is this point at every point what is its slope at every point along this curve? So back when we discussed instantaneous rate of change, we kind of threw in that word derivative. I went ahead and said it, and I said that's what we're going towards. And so we've arrived there now. So let's go ahead and let's make that definition. The derivative of a function f of x with respect to the variable x is the function f prime of x, and a little apostrophe right on that, f prime of x, defined as f prime x equal to the limit as h goes to 0 of f of x plus h minus f of x a over h, provided the limit exists. So right away this should be jumping out to us. This is our difference quotient, which we've said over and over again is just a slope of a line. Now we've stuck the limit with it because, like we saw with the instantaneous rate of change, if we don't have a line, it doesn't have a constant slope, and so we have to drive those 2 points infinitely close to one another, so that way we can get that slope at that single point. So what we see here is we see that slope of a point formula, but because we haven't said what x value we're looking at, we've generalized it just to be the point x. That means we're finding the slope at every single point along the curve f of x. We have found a derivative, but we've done it as a function. And so we'll see how this will work a little bit more in some of our examples. But I do just want to stress that provided the limit exists, there is that statement at the back end there, and that is important because not every derivative exists. And so we're going to see some examples of that as well. So I do want to just start with a very simple example, just so we get the hang of it. So let's find f prime. Clean that up a little bit. Let's find f prime of x for f of x equal to, we'll do 1 over x, so a rational function. So if we're looking at f prime of x, we are going to take the limit of our difference quotient. We're letting h goes to 0. As h goes to 0, the f of x plus h, we'd have 1 over x plus h minus the original function, 1 over x all over h. And so if we were to plug the 0 in right now, we'd get 1 over x minus 1 over x. That's just 0 over 0. And of course it would be, because if we're looking at when h is 0, remember how this slope worked. We're looking at two different points, really, when we're saying they're separated by a distance h. So if we're saying the distance between those 2 points is 0, they're the same point, they're going to give us a non-existent or impossible derivative, because we can't look at just one point to find that slope. We need 2 points, and they have to be separated by something. But like we saw with our limits, if we see that 0 over 0, that is an indeterminate form, and that tells us there's something else that can be done to this problem. And if we have fractions and fractions, the trick is going to be to multiply by the common denominator. So x plus h and the x, and we're going to do that top and bottom. And remember, we got to continue to write that limit in front until we actually evaluate the limit by plugging in. So if we multiply that first term, the x plus h is canceled, we'd only have the x left. When we multiply the second term, we have the x's cancel, we have the x plus h left. And then in the bottom, we'd have everything, because nothing is canceled, there's nothing in the denominator of the bottom. Now right away in the top, I should notice that the x minus x, they're going to cancel. The other thing I needed to do here, and I was really sloppy, this negative was in front, so when I multiply the x plus h to that x, I need to keep that in parentheses, because that h should also be negative, so really make sure you don't do what I just did, or at the very least fix yourself. We need to make sure we're distributing that negative to the h. And now, because I have all factors here, we've gotten rid of the terms by simplifying. I have factors, the h's will cancel. And that, of course, leaves me just a negative 1 on the top. And so we have the limit as h goes to 0 of -1 over x plus h times x. And as h goes to 0, this component goes to 0. However, there's still stuff in the denominator. So we're left with a -1 over x times x, which of course we can write that as an x squared. So we get -1 over x squared. And so that is the derivative of f of x. What we've done is we've created a new function, f prime of x equals -1 over x squared. So if we wanted to say graph that the same way, right, the f of x, we could have done any number of things with that. So we knew f of x was 1 over x. That would have looked like this. We could have graphed that. We can graph this f prime of x2, 1 over x squared. We should know what that looks like. And then because it has a negative front, that's going to reflect it across the x-axis. It'll look approximately like that. So we could graph it. The same way we can find f of 1 or f of 2 or f of 3, right? F of 1 we'd get 1 over 1 or just 1. F of 2 rather would get 1 over 2 or 1/2. We can do the same things for the f primes. We can do everything we could as if it's just a function, because it is just a function. So f prime of 1, that would be -1 over 1 or just -1 squared rather, still 1. F prime at 2, we get the negative, and then we'd have 1 over 2 squared, which is 1 over 4. And so we can find all of these values for any point, with one notable exception that I'll talk more about in just a second. But we can see that it's just a function. So, if this prime hadn't been there, we could have just treated this thing as a function, and we could have graphed it. We could have found all these values. We can do any number of things. We can find when it's increasing, decreasing, when it's greater than 0, less than 0, when it's equal to 0. Maybe it has x-intercepts, and maybe, as in this case, it does not. So everything we ever studied with functions, as a whole set of last math classes you've been taking, the 171s, 172s, calculuses, we can do all those same things on this function. Now, I did say that there's one notable exception here, because at 0 doesn't seem like we ever had values there, and that was true on the f of x too. So remember, there was that restriction that the limit had to exist, and so there are some points that limit doesn't exist, and so we'll talk about that a little bit more in just a second. But I do want to also point out that we can find the derivative at individual points, and we've done that here. So by finding the derivative as a function first, we have a function that can give us the derivative at any point. So now if I went on to ask a follow-up question of what is the derivative at 1? We plug in the 1 into the function we just created. What is the derivative at 2? Plug in the 2 like we just did. What is the derivative at 15? I can plug in 15. I can plug in -5. Whatever I want except for 0. I can find that derivative at a point by using the derivative as a function. So creating this is, in a lot of ways, more valuable than if we had just gone ahead and plugged in, say, the 1 at the start, right? Maybe this problem, instead of saying find f prime of x, had said find f prime of 1. Well, I could have put 1s in there at the beginning the whole time, worked through the problem the same way, but I would have one answer. I wouldn't have that function that can help me generate multiple values. And one last thing I'll note on this whole process is here we use the limit definition of a derivative, the formal definition of a derivative. We are going to see later on in this course that there are some shortcuts. We're going to have some rules for allowing us to find derivatives much, much faster. They're going to be nice, and they're going to make our life easier. But I do want to stress that we do want to be comfortable with this definition, because this is a definition. This is how things work. And so when we're developing our rules, if we don't have a definition, we're not going to know how to get to those rules. Or if we get to functions or things that fall outside of our rules, again, we need something that will always work. And so this limit definition of a derivative, that is our definition. That is how the derivative works. It's just going to be that later on we're going to also see some rules. And so we want to be comfortable with this definition. I do expect you guys to be comfortable with the definition. So in that last example, we saw that we didn't have a derivative at 0. So there are some times, clearly, when we don't have derivatives. So we're going to ask ourselves the question, when does the derivative not exist? And so we just saw one case. When we had that original function, we had a discontinuity at 0. We had something that wasn't defined, and it remained a problem with the derivative, and that's going to be true. The first case we're going to see that's an issue, discontinuities. if something isn't continuous, then there's clearly not a point to study. When we say the derivative, we are looking at this point. And so it's real challenging if two things aren't connected to look at that single point, because there may not be a point at all, as there is in this case. We have an asymptote, or it could be that we have something like a jump or a hole. So if I think about a jump, well, the function's doing two different things around it. That one point, so sure, this is a point that exists, but there's a jump there, right? We can't look at that one point and say there's the slope on both sides of that point is the same, because it's not. So if we were to draw the tangent line, it's not representing both sides of the point equally. Furthermore, holes, we can't study a hole because that hole just doesn't exist. So if this is at the value 1, just making up a number, if I say what's the slope at 1, well, there's no slope. It doesn't exist. That point never existed to begin with. So anytime we see discontinuities, that is an obvious case where we have something that does not have a derivative. Next, we could see that we are reaching infinity. And remember, infinity is an undefined value. So we could have something that looks like this. And right here, at this point right here, just for a second, that became vertical. The slope there became vertical. And so because that became vertical, well, we can't talk about a vertical slope. A vertical slope is undefined, and therefore that would not have a derivative. Or another way we can say that, it would be a vertical tangent line. So I'll put that in parentheses. It could be that as we approach a point, we see two different slopes. So unlike with the jump where it's just completely separated, right here we see, and I've drawn it as if it's becoming vertical. I don't even have to do that. So let me change it completely. Let's make it a little more of a slope, non-vertical slope. If we look here, if I were to look at the two tangent lines, if I were to look at the tangent line on the left-hand side, it would be this green line here. But if I were to look at the tangent line on the right-hand side, it would be this blue line here. Those are very much at odds, and so for that reason, we don't have a slope there, because there's two different slopes coming in. We can't look at the limit coming from both left and right and get to that consistent slope. So what this is called, it is a corner. And so we can add that to our list. Another type of point that doesn't have a derivative is a corner. Very similar to a corner, but slightly different, are cusps. And so cusps have those two different slopes too, but they're approaching the infinities. So this kind of ties into the vertical tangent lines as well, because they're becoming verticals. But cusps, anytime we're approaching those infinities, it looks kind of the same as a corner because it's sharper, but because they're approaching infinity, we just rename it slightly differently. Other things that we might see, we might have a wild oscillation. And so as we approach a single point, it could be that it just gets so crazy what's going on there, we can't really track what it's doing, and then maybe it spreads out again. So every point outside of that, except for the vertical points, we'd be fine at. It's just there in the middle, the wild oscillations, we can't find the derivatives there either. So these are kind of the things that we want to be on the lookout for visually to know if a point is differentiable or not. But when we come to the equations, we need to be able to find those derivatives. That is the key. And so for our first example, we very clearly saw that we couldn't have 0 in the denominator. That is a point where we couldn't have a derivative. We didn't have a derivative at 0. If we look at a piecewise function, so let's take the function f of x, and we'll define it as x plus 2 if x is less than negative 2, and it's equal to x squared if x is greater than or equal to negative 2. And so there could be any number of reasons that there is a discontinuity in this, or sorry, a point that's non-differentiable is what I meant. So there is a non-differentiable point because of the discontinuity, but that is one potential reason. Could also be that the slopes don't match. So we'll look at both kind of cases. So the x plus 2, we know what this looks like. This is a line. We can find that derivative. Let's go ahead and do it. So let's find the derivative of x plus 2. I'm going to look at the derivative for f of x. And in order to do this, we're going to have to define it piecewise. And so we're going to look at the x plus 2 first, and we take the limit as h goes to 0 of x plus h plus 2 minus x plus 2 over h. And this is only going to be true if x is less than negative 2. We're also going to look at the limit as h goes to 0 of x plus h squared minus x squared over h. And this is true if x is greater than, I'm not going to put the equal to 2 in there yet because we'll have to discuss that point. So if I find this derivative here, we can see the x plus 2's cancel out, the h's would cancel out, and so all we'd have there is a value of 1. That's, again, if x is less than negative 2. Because we could find that derivative. Everywhere on there we can find that to limit, right? Everywhere in this function the limit exists. That's if x is less than negative 2. If h is going to 0 of this guy, we can FOIL this out. We'd have x squared plus 2xh plus h squared. The x squareds would cancel, leaving us a 2xh plus h squared over h. That's true if x is greater than negative 2. Again, I'm holding off on the writing the equals to because I don't know. Equals negative 2. I don't know what's going on there. And so when I simplify that, I get 1, and I get, for the bottom function, the h's would cancel 2x plus h. And because we're taking the limit, I drop my limit, and I shouldn't have. Because we are taking the limit as the h goes to 0, I'll cross these h's off. As that last h goes to 0, we're only going to be left with the x. And so then this is true if x is less than negative 2. But what I really care about is what about the negative 2? So I've found the slope equations for both the line and the curve, and I know those have to be true if x is greater than negative 2 for the case of the 1, and then has to be true of the x less than negative 2 for the 2x. Clean this up a little bit, shift that down. Shift it up rather. So this, the 1 is true if x is less than the negative 2, and then the 2x is true if x is greater than negative 2, but what about at the negative 2? And so the first thing I see is if I plug the negative 2 into both of these, the first one I would get a slope of 1. And then the second one I'd get a slope of negative 4. And so as I'm coming to that single point, we have a problem. We have the slopes not matching up. And so for that reason, this function doesn't have a derivative at negative 2. But actually, this was a lot of work for naught. A lot of extra steps that I didn't need to do because I could have looked at the negative 2 right away and been able to see it didn't have a derivative. Because if I just look at the continuity, if I plug negative 2 in, I get negative 2 plus 2, which is 0. Negative 2 squared is 4. And so because negative 2 is a non-continuous point, I've found the derivatives to the left and the right of it, but I know that the derivative does not exist at -2. So does that mean that piecewise functions will always have discontinuities at the piece where they are supposed to overlap? And that's not true either. So let's take the function x plus 3, and that is true if x is less than 1. And let's take our second equation, the square root of x plus 3, and that is true when x is greater than equal to 1. So again, we have a piecewise function. Does that mean it's guaranteed not to have a derivative transition? Now we could very easily find the derivative of this equation. They are differentiable where they exist. So for instance, here the domain is from 0 to infinity. But that's perfect because x is greater than 1. That's not a problem. So we do know that this thing would be differentiable on each of the independent domains. But what about where they overlap? So is g differentiable? I'm going to abbreviate that DIFF at x is equal to 1. That is our question at hand. Well, I could go ahead and do all the same steps as I did the last one, find the derivative from the left, find the derivative from the right, but if I could show it as discontinuous, we said before that's a lot less work. Once we see that it's discontinuous, we could stop right away and say, hey, it's not going to be differentiable. So let's check to see, is it continuous? And so remember the steps for continuity. We need to find the limit exists, we need to find the function exists, and we need to show that they are the same. So I'm going to start by finding the function value just because that seems like it's easier. If that doesn't exist, it makes my life a lot faster. So g of 1 would be equal to the square root of 1 plus 3 because we look for where it's equal to. That's the bottom equation. And 1 plus 3 is 4. Next, I'm going to look for the limit. So we're going to look for the limit as our x is approaching 1. And to remember to show the limit exists, I have to show from the left and from the right. And so the left means I'd be using the top equation, the x plus 3. And so we'd have 1 plus 3, which is equal to 4. And then we still have to do the limit from the right to show that they're the same. The limit as x approaches 1 from the right, we'd have to be using the square root of x plus 3. So we'd have the square root of 1 plus 3, which is still equal to 4. So now we can state with confidence the limit as x goes to 1 of our function g of x is equal to 4. We know that because both of the one-side limits exist. So remember, we did this back in one of the earliest videos. In the earliest stages of class, we had to show that a limit existed. It requires us showing the left and right limits are the same. Then we can make that statement, limit exists. So we do need to show all of that to show the limit exists. We've also found the function value. We found that to be 4. And so now we can state we know that g of x is continuous at x equals 1 because the limit and function exist and they are the same. So again, this is what we did earlier on in the course as well. We're just kind of combining those skills, we're building on it. But we still have to show that the derivatives from left and right are the same. So I'm going to look at limit as h goes to 0 of our upper function, which was just the x plus 3. So I'll have x plus h plus 3 minus the x plus 3 all over h. And so when we find this limit, the x plus 3's would cancel, so we'd have h over h, and that is equal to 1. Okay, it better be the same as the slate from the other side, so we're going to have to look at limit as h goes to 0 of the square root of x plus 3. So we'd have the square root of x plus h plus 3 minus the square root of x plus 3 over the h. So if I were to plug in right now, I'd get square root of x plus 3 minus square root of x plus 3 is 0 over 0, which we would expect because derivatives will always give us that 0 over 0. So that tells us we have to do something else. The first thing that I need to do here, one of our tricks we used when we were doing limits is we said if there are square roots in it, we're going to have to multiply by the conjugate. That is true, but there can only be a conjugate if there are two distinct terms, and here we have 4. So notice I can cancel out those 3's first. That is an important first step. So now we have the limit as h goes to 0 of the square root of x plus h minus the square root of x over h. Still giving me 0 over 0, but now I have the opportunity to multiply by the conjugate. So we're going to multiply by the square root of x plus h plus the square root of x. We're going to do that on the top and on the bottom. And so when we multiply those square roots to one another, get that x in there. When I multiply those square roots to one another, they are just going to cancel out, leaving what's on the inside. So we will have the limit as h goes to 0 of x plus h times x plus h is x plus h when we drop those square roots. Square root of x times square root of x gives us minus x over. Now we have the h down there, we have the x plus h, and the plus square root of x. The square roots do need to be in parentheses because the h would have to be foiled or distributed, not foiled, but distributed to each of those terms. Now I can cancel out the x's on the top because we have x minus x, and so we're left with an h on the top. We have that h on the bottom, which, because we worked those parentheses, is a factor and not a term. So rather than distributing, I can just cancel those h's off. And I'm left with the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. And so when we take our limit, we get 1 over 2 square roots of x. Now, I wanted to know the derivative at the point 1. That was the one in question. Is it differentiable at 1? So I could have plugged in the 1 at the beginning, but as we've discussed earlier in this video, if I find the derivative as a function, I have that function, and I can plug in whatever I want. So now I want to know what is the value at 1. And so just plugging in that 1, we would get 1 over 2 square root of 1, which is 1/2. And now we see that the derivative is certainly not the same at 1 and at 1/2. So this one took a lot more work than the last one. The last one is a lot easier just to say, hey, this thing is not continuous because, or this thing is not differentiable because it is not continuous. Here we actually had to find those derivatives, and then we could state that they were not continuous. Now, again, this makes it look like piecewise functions are not going to be differentiable at their point of intersection, and that is also still not the case. So we could do yet another example. Let's take h of x to be 2x if x is less than 1, x squared plus 1 if x is greater than 1. Is h of x differentiable at x equals 1? So we've seen two other piecewise functions that weren't, one because it wasn't continuous, one because it wasn't differentiable. Let's look at this one. So first thing I'm going to check is it continuous? So I need to start by finding either the limit or the function value. I'm going to look for h of 1 first, which would be 1 squared plus 1, which is equal to 2. It does have a function value. Next, I'm going to look at the limit. So I'm going to look at the limit as x approaches 1 from the left, meaning I'm using that top equation, so the 2x. And I can plug in there and have 2 times 1, which is 2. Then I'll look at the limit as x goes to 1 from the right. And so that means I'm using the x squared plus 1. So we'd have 1 squared plus 1, which is also equal to 2. So I can state at this point with a surety, well, I need to actually state the two-side limit first. Let me do that. Because we know that these left and right limits are the same, I can state that the limit as x goes to 1 of our function h of x is equal to 2. So now we can make the statement h of x is continuous because the function value and limit value are the same at x equals 1, which obviously implies they both exist. So next we need to find those derivatives of both of these. So we'll start with the 2x. the limit as h goes to 0. Notice we're using the limit in both the limit cases and on our difference quotient. We're doing it for two different reasons. We're finding the limit here to prove continuity. We're finding the limit here of the difference quotient to find what that slope is actually coming in from the left. So I'm going to take the 2x first. So we have 2 times x plus h minus 2x over h. I need to distribute that 2 first. So we'd have the limit as h goes to 0 of 2x plus 2h minus 2x over h. We can cancel out those 2x's first, then we can cancel out the h's. And as that h goes to 0, it doesn't matter because there's not an h left in the problem. The answer is 2. Next time I'll look at the limit as h goes to 0 for the second half. So that would be the x squared plus 1. So we'd have x plus h squared plus 1 minus x squared plus 1 all over h. And so if I want to, I can cancel off the 1's right away, but the x squareds I can't because I do have to multiply this out or fully distribute that. And so we'd have the limit as h goes to 0, x squared plus 2xh plus h squared minus the x squared all over h. So now I see some things that cancel. The x squareds will cancel, and I can take an h away from every term because now there's only h terms left. We could also factor out the h on the top. So now I have the limit as h goes to 0 of 2x plus h. And so obviously as h goes to 0, we're left with just the 2x. And so we're curious about the derivative at the point 1. And so when we plug that 1 in, we get a derivative value of 2. So now what we see is that the slope is the same from left and right. So we can state h of x is differentiable at x equals 1 because it is continuous, and the slope from left and right is the same. So that's kind of what the question, does the derivative exist, all boiled down to. If we come all the way back up here to when we defined what gives us a non-differentiable point, discontinuities, and all 4 of these others are really things where the slopes aren't the same. Now, the vertical tangent line, we'd see that we have that undefined slope. That's another thing we want to be on the lookout for. If when we try and find the slope, we get an undefined value because the limit just doesn't exist, that's leading us to believe it's some sort of vertical tangent line or some sort of oscillation that we don't know exactly what happens. But corners and cusps, those are both just points at which the slope is different on both sides. So we want to be on the lookout for discontinuities, just is it possible, and then are the slopes the same on both sides? And that will show us that we have a differentiable point, and moreover it can show us that we have a differentiable equation. So piecewise functions, one of the weird ones where we have to test those transitional points. Other functions we need to just pay attention to, well, did that point exist to begin with? So for instance, back here on the 1 over x, 0 never was included, so that's a discontinuity. That's something we don't need to ever consider. And to the left, to the right, can we find its derivative? Yes, we did. We know that those points would be fine. We're going to continue working with these derivatives, and we will see how we can apply those rules to make it a little bit easier for us. How can we speed ourselves up in finding these derivatives?